It's winter. A quiet lake sits under the pale glow of the moon. The air temperature plunges below zero. The surface of the lake freezes, but instead of sinking like most solid materials do, the ice floats. And that single bizarre behavior is the reason life on Earth survived. Why does water expand when it freezes? Almost every other substance in the universe does the exact opposite. In general, when liquids freeze into solids, their molecules slow down and pack closer together. Think about molten metal cooling into solid steel. The atoms lose energy, settle down, and lock into tight, compact structures. That makes solids denser than their liquid forms. But when liquid water freezes into ice, it actually expands by about 9% in volume. That expansion lowers its density, which is why ice floats. To understand this, we have to zoom all the way down to the molecular level. A single water molecule, H2O, is made of 2 hydrogen atoms and 1 oxygen atom. But the arrangement is the key. Instead of forming a straight line, water molecules form a bent shape like a wide V. The oxygen atom sits at the top, and the 2 hydrogens attach at an angle of about 104.5 degrees. That odd shape gives water something important: polarity. The oxygen side carries a slight negative charge, the hydrogen side carries a slight positive charge. So every water molecule is like a tiny magnet. And magnets love to stick to each other. Because of polarity, water molecules attract each other through something called hydrogen bonding. These aren't full chemical bonds like the ones holding the molecule together. They are weaker intermolecular attractions, but in huge numbers they are incredibly powerful. In liquid water, molecules are constantly moving. Hydrogen bonds are constantly breaking and reforming. Everything is chaotic and dynamic. The molecules are close together, but not arranged in any rigid structure. Now watch what happens as temperature drops. As water cools towards 0 degrees, molecular motion slows. Hydrogen bonds begin to last longer. And when water finally freezes, the molecules lock into a very specific structure, a hexagonal crystalline lattice, a honeycomb-like pattern, an open spacious arrangement where each molecule forms hydrogen bonds with 4 neighbors in a tetrahedral geometry. That structure actually holds the molecules further apart than they were in liquid form. Instead of squeezing together, they spread out. That open hexagonal structure creates empty space within the crystal. More empty space, less density. Lower density, floating ice. Water actually reaches peak density at 4 degrees centigrade, then begins expanding before it even turns to ice. It's backwards from almost everything else in nature. Now imagine if water behaved normally. Imagine if ice were denser than liquid water. When lakes froze in winter, the ice would sink. New ice would form on top and sink again. Over time, entire lakes would freeze solid from bottom up. Marine ecosystems would collapse every winter. During the ice ages, oceans might have frozen completely. Life as we know it might never have survived. But because ice floats, it forms an insulating layer on top of lakes and oceans. The liquid water below stays warmer. Fish survive. Ecosystems persist. This single molecular quirk protects life on Earth. You have probably seen this effect in action. A soda can bursting in the freezer. Pipes cracking during winter. Ice wedging rocks apart in a process called frost weathering. When water seeps into cracks and freezes, its expansion exerts enormous pressure, up to 30,000 pounds per square inch. Over time, that force can split mountains. Now, why this doesn't happen to most substances? Because most substances don't rely on hydrogen bonding. Their molecules interact primarily through weaker van der Waals forces or stronger metallic or ionic bonds that pull particles closer in solid form. Other substances that form hydrogen bonds, like ammonia, can show unusual behaviors too, but none match water's dramatic density inversion. Water's molecular geometry is almost perfectly tuned to create this anomaly. Scientists have reached for water across the solar system because its physical properties stabilize environments. Floating ice regulates planetary climates. Its high heat capacity moderates temperature swings. Its expansion upon freezing prevents total oceanic collapse. Water isn't just common, it's weird in exactly the right ways.